In this lesson, we're going to talk about RAID. RAID stands for Redundant Array of Independent Disks. It's basically a way to logically connect two or more hard drives or solid-state drives and one or more controller cards together as a single storage system. We do this to improve system performance and create data redundancy. Let's take a closer look. When you implement RAID, you do so using either hardware or software. To implement RAID using hardware, your system must have a physical card known as a RAID controller. Many servers come with a RAID controller built into the system, but for those that don't, you'll have to purchase a card and install it. RAID controller cards have their own processors dedicated to managing RAID arrays. This provides the greatest flexibility for different types of RAID configurations, although it's initially more expensive. With software, instead of using a RAID controller card, the system CPU and operating system create and manage the array. Today, CPUs are powerful, so generally there's not a performance hit. Software RAID works well and numerous operating systems support it. One of the major benefits of a software RAID is that it's easy to implement and a lot less expensive because you don't have the cost of purchasing a new RAID card. However, it can be a bit slower. Using either method works, but if cost isn't an issue, we always recommend going with hardware RAID over software. To better understand why, you'll need to understand 4 critical RAID concepts and how they apply to the common RAID levels you'll encounter. Our first concept is disk striping, also known as RAID level 0. When you implement striping, the data is divided up and written across 2 or more disks simultaneously. This gives you blazingly fast read-write performance. The drives don't have to be the same size, but the storage space added to the array by each disk is really limited to the size of the smallest drive. In this example, we have a RAID array that contains 2 disk drives. With striping, when data needs to be written, it's split up with data being saved on one disk and different data being saved on the other disk. But the data is written to both drives at the same time. Even though you have 2 disk drives in the striped array, the operating system sees them as just one logical drive. The 2 drives work together as one. If you have 2 heads on 2 different disk drives, each reading and writing half the data, theoretically you can read and write data twice as fast. In practice, it's not quite twice the speed, but it's close. Striping across many disks can dramatically increase the speed of your disk I/O operations. Striping has some great benefits. The total array capacity is the sum of the capacity of each disk. However, there's a big problem with striping, and that's that if just one of the disk drive fails, the entire array fails because the data becomes corrupt on all the disks. Just remember that the 0 in RAID 0 literally means there's 0 redundancy and 0 fault tolerance. Each additional drive creates another failure point, which basically increases the odds that someday the array will crash. The next concept is mirroring, or what we call RAID 1. Mirroring doesn't speed things up, but instead, it helps protect the data by providing redundancy. With RAID 1, the 2 disks become mirrored copies of each other, with both containing the exact same files and folders. And just like with the striped array, the operating system sees these 2 mirrored drives as one logical drive. In a mirrored array, a piece of information that needs to be written to disk is written on both drives at the same time. The data isn't split up like with striping, but a full copy is written to both disks instead. The advantage of mirroring is that if something were to happen to one drive, the data would still be okay because an exact copy is written to another drive. In fact, most RAID systems are configured so that if one drive goes down, the other automatically takes over and the users never know anything ever happened. They'll keep doing what they were doing, but now their work will only be saved to the good drive. Mirroring is great, but there's still a single point of failure. When you set up mirroring, you use one RAID controller to manage the mirrored drive array. If the RAID controller were to fail for any reason, you'd lose all your data. Even though it was mirrored, both disk drives would no longer be operable. To get around this, you can implement duplexing. Duplexing looks a lot like mirroring, but with an extra controller card. You still have 2 disk drives, but instead of connecting them to a single controller, you connect each one to a different controller. As with RAID 1, the operating system sees them as one logical disk. When data needs to be written, it's written to both disks at the same time, just like with mirroring. The difference is that it goes through 2 different RAID controllers. If one controller goes bad for some reason, your disk I/O operations would still work. Users wouldn't notice any difference either, because the working RAID controller would take over and continue servicing requests. You can use the system this way until you have a chance to replace the other controller and rebuild the mirror set. As you can see, disk duplexing provides you with both redundancy and fault tolerance. An important RAID term you should understand is parity. Mirroring and duplexing work nicely, but you don't get the speed advantage that striping provides. Parity is simply a calculated value that's used to mathematically rebuild data in case of a failure. You can store this on just one drive called a parity drive. More commonly, though, the parity gets striped across all the drives for speed, redundancy, and fault tolerance. We call this configuration RAID 5, and it requires 3 or more drives to implement. Generally, it's best practice to have these drives all be the same size and speed to achieve the best performance. When you set up distributed parity, you set up a striped array across multiple disks. Notice that a portion of each disk is reserved for parity information. This is what provides the redundancy and fault tolerance. In the case of any single disk failure, the parity information stored on the other drives can be used to reconstruct data for the failed drive. The array will continue to work, but performance will be slower until you replace the failed drive. That's why it's a great strategy to have a hot spare ready and waiting in the array, because sooner or later a drive is going to fail. And if one drive does fail, the hot spare becomes the failed disk. But keep in mind that if 2 drives fail, the RAID 5 array becomes completely corrupted and unrecoverable. Because of this, RAID 6 is becoming more popular since it adds another layer of parity that can tolerate 2 drive failures. Notice that if you add up all the distributed parity information across the array, not including the hot spare, it's the equivalent of 1 whole drive in the array. This means that if you have 5 drives, as in this example, your overall logical drive capacity will really be the sum of only 4 drives. So if each disk is 5 terabytes, the total usable storage in the RAID 5 array will be 20 terabytes. It's always the number of drives minus 1 to determine capacity. The last configuration we're going to discuss is RAID 10, also known as RAID 1 plus 0 or RAID 1 and 0. It uses striping and mirroring and requires a minimum of 4 disks. With RAID 10, the data is striped across the mirrored pairs, which provides redundancy and high performance. RAID 10 is your best choice when you have applications that require fast read-write operations like databases, email, web servers, or any other system requiring high disk performance. That's because RAID 10 doesn't have to manage parity. In fact, RAID 10's read performance is actually twice as fast as RAID 5, and as long as one disk in each mirrored pair remains functional, data is always retrievable. But if 2 disks in the same mirrored pair fail, all the data in the array will be lost. Another disadvantage is that only 50% of the total raw capacity of the drives is usable due to mirroring. You should know that a non-standard definition of RAID 10 was created for the Linux MD driver called Linux RAID 10, in which arrays of 2 to 4 disks are possible. There are also other RAID levels besides those we've talked about here, but these are the common ones. Well, that's it for this lesson. In this lesson, we discussed how you can configure a RAID system using hardware and software. Then we discussed disk striping, mirroring, duplexing, and parity. And we matched each of these technologies to their respective RAID levels, RAID 0, 1, 5, and 10. Depending on what you're looking for, a RAID configuration can bring you the speed, redundancy, and fault tolerance you need.